Here's one last video with a bunch of examples of osculating circles, just because they're fun to look at. So here's the parabola again, with the curvature and the osculating circle shown, so you can get an idea of how this circle is the circle of best fit. It seems to approximate the parabola pretty well at various points. So that's not a tangent line, but it's some sort of approximating circle. And so notice on the sides, the parabola is really flat. That circle has a huge radius, and the curvature is in the hundredths. And so the radius of that circle at this point is 1 divided by 0.02935, and that's an awfully large radius. On the flip side, the curviest that we get is here at the vertex, where the curvature, well, if I were exactly at the vertex, it would be exactly 2. And sure enough, the osculating circle has diameter 1, so it has radius 1/2, 1 over the curvature. So let's look at a few others. The cubic, something really cool happens. Watch for it right in the middle. The osculating circle switches sides. And that's because it's an inflection point of the graph. And so the circle, instead of opening downward, has to open upward if it's going to actually fit the graph and be a good approximating circle. I showed you the quartic before, so let's see that one really quickly. So the circle starts off really large, gets small, large, small, and so on, because the curvature keeps bouncing around. And then last week we also looked at ellipses and some other things. So the ellipse is curvier at 2 of the vertices than the others. Or instead of 5 cosine t, 3 sine t, if I put the 5 and 3 inside there, remember we get this cool looking curve. Computations are a little worse here, so Mathematica is going to have to think about it for a little while. Let's slow this down just so you can actually see some of it. And notice the osculating circle, like right there, switches sides. We don't have a notion of inflection point per se for a curve like this, but this actually gives us a way that we could describe that. The curve changes from turning to the left to turning to the right, and the osculating circle has to switch sides. So the curviest part on this curve would be in one of these corners here, and we'll see how close I can get. So curvature is 33 right there, so that osculating circle has a radius of 1 divided by 33. And finally, let's look at this shape that had a cusp in it, cosine of t, sine of t cubed. And this one it really has to think about. So this gives you an idea of just how involved some of these computations can be, but it will eventually give us something. So you can see this one has lots of these inflection points where the osculating circle switches sides. And because of that cusp, weird things happen at this cusp. Watch the curvature. 5, 7, 9, 12, 17, 22, 158. So that tiny little dot there is actually an osculating circle of radius 1 over 158. And depending on where it lets me actually move that slider, I can get it even higher. So there's something with this cusp that the curvature seems to be increasing without bound, which means the radius of the osculating circle goes down. Alright, CalcPlot3D can also plot osculating circles. I'll make sure Professor Bright knows how to do that. But it means you can yourself look at 3D examples of this, like a helix, which like a circle has constant curvature, and so that osculating circle moves around, tilts up, tilts down, and so on, but it always has exactly the same radius. Or here's an elliptical spiral kind of thing. So it stretches out 4 units in one direction, 2 units in another, but it's also moving up the whole time. So I'd encourage you to spend some time with CalcPlot3D or other programs that can plot osculating circles and explore, see what you find. There's some really cool things you can do.